ELRs 2.4 and 2.5 are about momentum and the conservation of momentum. For both of these, we need the equation for momentum. So momentum is mass times velocity. And we're going to use that a whole bunch all throughout these two ELRs and actually into the future too. So the first one's saying, what is the momentum of a 50 kilogram object with 30 meters per second? So it's as easy as they come. We're solving for momentum. We don't know what that is yet, but we do have our mass and our velocity. So mass is 50 kilograms, and we have to multiply it by our velocity, which is 30 meters per second. And 50 times 30 is 1,500. And our units for these are a little bit weird since we're doing kilograms times meters per second. Our unit is kilogram meters per second. For number 2, in your own words, what does the law of conservation of momentum say? So the law of conservation of momentum is whatever momentum you start with before a crash is the same as the amount of momentum after a crash. Momentum can be transferred from one object to another, but it's never going to disappear. It's got to go somewhere. For number 3, you throw an 8 kilogram bowling ball to your friend. Your friend, who is just standing there minding his own business, catches it and starts moving at the velocity of 0.3. So we need to find the mass of our friend. For this one, we need to be able to set up a before and after table. So I'm actually going to scooch this down and use the space down below. So for our before and after table, we need before, we need after. And what we're doing is we're making a table that shows all of the momentum before, and we're going to compare it to the momentum after. Since we have two objects, we have the bowling ball, so I'm going to put ball and friend. And then of course we also need a row for the total. And now we're just going to be able to fill in some blanks. And each one of these squares is going to have momentums in them. So again, momentum is mass times velocity. So the bowling ball before says that the bowling ball has a mass of 8 kilograms. And so we can plug that in right here, 8 kilograms. And in these kinds of equations, the mass of the objects is never going to change from before to after. So after, it's also going to have 8 kilograms. And it says that we throw the 8 kilogram bowling ball to our friend at a velocity of 2.1. So we have the before velocity also. So put some parentheses, 2.1. So we have our mass, we have our velocity. We can solve for that momentum, but I want to keep plugging in some information so that we can get all of our pieces pulled from the question. It says our friend who was just standing there. So we know the velocity of our friend was 0 meters per second. So I'm going to put that in for the before. Catches it and starts moving at a velocity of 0.3. So if the friend catches it, that must mean that they're moving together. So I know that the bowling ball after has 8 kilograms and is moving at 0.3 meters per second. So I have all the pieces for the bowling ball now. And since the friend caught it and was moving at 0.3, we know that's going to be my friend's velocity as well, meters per second. And it says, what is the mass of our friend? So we don't know the mass, and that's the one variable that's missing. So I always like to use the letter that reminds me of what I'm solving for. I'm going to use mass of friend. That's just a little f to remind me that it's not the ball, but the friend, because sometimes I forget by the end. So now I have all of the pieces, even though some of them are variables. So I need to go 8 times 2.1, which is 16.2, no, 16.8. So we have our momentum of the friend, the momentum of the friend is mass times 0. So even though that's a variable, anything times 0 is going to be 0. Now I have the ability to figure out all of the before momentum. So let me grab a different color. We'll go green. So all of the before momentum is the 16.8 plus 0, and we're going to put our total down here. Same thing's going to happen on the other side. I'm going to add up whatever these two numbers end up being and put my number down below. And then what I end up doing is I set them equal to each other. So let me go back to my pink pen. Okay, so 16.8 plus 0 is, of course, 16.8. Then on the other side, 8 times 0.3 is 2.4. And the mass of my friend, which we don't know, times 0.3 is just 0.3 mass of friend. So those two things added together. The second biggest mistake that I usually see is some people are going to try to add 2.4 and 0.3, but those are not like terms. So make sure that you are keeping them separate. So we're going to have 2.4 plus 0.3m. Now we just have an algebra equation. I need to subtract 2.4 from both sides. And then once I've subtracted, I'm going to divide by 0.3. When I do all of that, I find out that the mass of my friend equals 48. Now at this point, I sometimes forget what I was solving for, and that's why I left it as an m. So mass is, of course, kilograms, and that is our final answer. For number 5, it says 2 pistols are shot at each other, and the bullets collide in midair. So we're going to have another conservation of momentum problem, so I'm just going to get started setting up my before and after table. And we've got 2 bullets, so since they're both bullets, we're going to say bullet A and bullet B, it looks like. So I'm just going to put A and B and total. And now we have all of the makings of our table. And just like before, we're going to fill in all of the momentums into these boxes. So I start by going through the entire question and plugging in the things that I know before I do any calculating. So they shot each other, they collide in midair. Bullet from gun A has a mass of 0.2, or excuse me, 0.02. So 0.02, losing all sorts of things here, 0.2, okay. And bullet B has a mass of 0.05, so 0.05. Okay, if these two things are going to hit each other in our physics class, they're not going to change mass. So after, it's also going to have a mass of 0.02 and also 0.05 for bullet B. And they both leave their guns at 150 meters per second. Now here's the trickiest part of this question. If they're being fired at each other, one of them must be going this way and one must be going that way. It doesn't matter which one you assign to a positive number and which one you decide to make a negative number. You can make the one going to the right positive, or you can make the one going to the left positive. It doesn't matter as long as you stay consistent throughout your problem. So I'm just going to say that bullet A is the one moving in the positive direction. So it's going to have a velocity of 150. And then bullet B, of course, because it's moving in the opposite direction, has to have a velocity of negative 150, since it's in the opposite direction. And then it says when they collide, what would be their velocity after they hit? So when they hit each other, it sounds like they're going to be sticking together. So we're going to have the same velocity for both of these. So we're going to say velocity just in general, velocity after. Now we have all of the parts and pieces. We can start solving. So 150 times 0.02 is 3. And then negative 150 times 0.05 is negative 7.5. Don't forget that negative sign. And then we're going to add these two things together because it's all the momentum before. So when I add these two things together, the next common mistake that I see is somebody's going to try to pretend that this wasn't negative anymore. So a negative 7 and a positive 3 are going to take us down to a negative 4.5. And then on the other side, we're going to have 0.02 Vs and 0.05 Vs. And so these two things added together are going to give us 0.07 Vs. Now we just need to divide both sides by 0.07. And after some rounding, it looks like we're going to get 64.3. 64.3. Again, don't forget your units. We're solving for velocity, so that's going to be meters, negative 64.3 meters per second. So the negative sign is telling me that it's going in the same direction that bullet B was originally going at the beginning. And that is our final answer for that one. So now you may have noticed that I skipped question number 4 a little bit ago. What is the example of an elastic and an inelastic question? That's because we have just solved a couple of those types of questions. So an inelastic collision is when they stick together, the two objects. And actually both of these have been examples of inelastic because the friend caught the bowling ball and they stuck together, and the two bullets hit each other and stuck together, so those are both inelastic. If you were to take a bouncy ball and bounce it off the floor, that would be an example of an elastic collision.